Okay, got some sound. Let's see who just joined me. Glad to see you, Colton. Glad to have you aboard. And as I mentioned, everybody, I we all should be here if we're going to. Everybody should be logged in and because it's a class session. But I've got a few people who are traveling, athletic events, or traveling home, whatever. So, but the video is going to be posted as usual. So I'm going to get us started, and glad to see you as well, Sarah, and over here in Moodle. And I'll pop down and talk about what we've got going on now. Here this week, we started, and regrettably, Monday, we had some issues with the drivers on my machine. We've all gotten new, those of us who wanted them, Dell computers, and the drivers are all loaded online up in the cloud, and the folks over in IT simply are just kind of waiting to find out whose computer failed. So mine failed, unfortunately, in a class, and I apologize for that, but I did post I did post a lecture, so that's there for all of you to see. Now, we have a couple of things we're going to do today, and I want to start first with par nonlinear. And par nonlinear is over in the Anderson text, the big one, and we'll take a look at that. So I'm going to move this jewel over for just a moment. I'll go back to the vital source. And now this is the data smart text, but I want to look at the Anderson first of all, and we'll go in and we'll talk about that real quickly. And again, par nonlinear is covered on pages 371 to 378. And the par nonlinear file is in the Anderson student files, and that shouldn't be a big surprise for you now. And I'm going to search the contents of the book, par nonlinear. See if it's going to play nice with me. If not, I'll put in the chapters for the book. And that's down here. Here we go. And I believe it's 368. There we go. Now, okay. I guess, yeah. All right. Now, we're going to talk, I want to spend just a bit of time talking about par nonlinear. Now, this opens up the chapter, and the authors talk about what do we mean by a nonlinear problem. And what they basically say is that, and they give us this definition right here, it's an optimization problem in which at least one term in the objective function or a constraint, is nonlinear. And so what we're saying is in English that the area the region of feasibility, or the feasibility area, does not conform to what we see when we have a linear trend. Okay, it will tend to be either concave or convex. And if I'm not mistaken, in this week's readings or resources, I had a link for you explaining the difference between the two of them. Let's forge on ahead here, and we'll take a look. And this is Par Inc. Revisited, okay? And here they have a non-constrained problem. And so they're producing, I think there's still these golf bags. Some are standard, some are deluxe. All right, and we get some, and we start to build some of the constraints in, and we start to look at total profit contribution. And then they give us par in terms of a constrained problem. and they give us a solution, right? Again, when we're working with a nonlinear objective function, it doesn't look like the feasibility region. Now, if you were to go back to some of the earlier cases and look at the feasibility regions in those figures, you're going to find that it fits. Now, I'll just do the little annotation thing right here. Myself a drawer. It doesn't fit a strict linear trend, okay? Instead, what we see is this business over here where we have something that kind of looks like a little plateau, and that's telling us that we have and we have a point outside where we can identify an unconstrained optimum. Now, to do the algebra, the linear algebra, to get here is going to be lots of iterations, a lot of time. So the solver and any other tool like it you're going to be using will give you an opportunity. Pardon me, not opportunity. Excuse me, but it will show you that you probably ought to be working with a non-constrained model. Now, you're going to come to that conclusion if you do any algebra anyway, and you may come to that conclusion if you're just looking at the data and you've worked with the product or service enough that you know that you have an unconstrained optimum. In other words, you can go ad infinitum. Now look, let me stop for a moment and talk about this little critter right here. Okay. Let's see. I don't want to do that. I'm going to do that, and I'll do a circle. Okay. Now, this optimum may or may not be feasible in a practical sense. So what do you mean? We may have an unconstrained optimum, but we may not have the facilities or the supply chain to meet that objective function. In other words, to produce that much profit. It may be beyond our ability in the real world to do it. Now remember now, what we're doing here in management science is we build a model and we use that model to look at the possible outcomes. And when we get these kinds of too good to be true, then we're working in a non-linear world, and that becomes one that's far more practical. It looks far more like what we would see out in the real world as opposed to this straight line here. And so it's a subtle shift in your thinking. Now you say, well, we'll gear up. Now, a company could say, well, that's wonderful, and we'll gear up to do this. We'll expand our plant. We'll expand our manufacturing, the workforce, etc. Well, that becomes then the optimization problem then moves from being one of optimization to a capital budgeting problem. And so it moves from kind of the theoretical to the less theoretical, a little bit more practical. And that's when you have to really do your homework. I included the part on linear. We've worked with PAR before, and they're manufacturing the bags. And the file is there in the Anderson Chapter 8 files, and we'll look at it for a moment. But I want to make sure you understood conceptually what we're talking about. Now, there are many, many firms who really operate in that basis, and could have an unconstrained optimum. Now, you say, well, Dr. Herman, what would stop me from saying, okay, what I want to try to do is make this a long-term objective and I want to build the company's capability to that point. Okay? That's fine if you've done some homework in terms of looking at your competitors to say, okay, what will they be doing in the future? So this is the nonlinear is in a sense more practical than the linear functions we've been dealing with. Okay, and I'm going to go back over here to my little drawer, and I'll close that off here for a minute. I'm enjoying, and I hope you're enjoying the little annotation deals I got going on, because now I'm going to show you something cool. This is, again, the spotlight. Okay, isn't that cool? What can I say? I want to add value for your learning every single time I get. Now I'm going to close this off, and then I'm going to do the eraser. Let's see, I want annotation. I want the eraser. All right, there we go. Now, we're going to come down here to figure 2, okay? And here's the solution for the nonlinear. Now, this is in the I believe this is the lingo, and here we can see the objective value. And we can see that what we get in terms of the standard bags versus the deluxe bags. Do we reduce any costs? No. But notice something. If we look over here, and this is when we talked about where we just got through mentioning this unconstrained optimum. Theoretically, okay, we have first of all, on our first constraint, for every change in it, we get 26 additional value. That's the dual value again, or the shadow price. And if you look, you're going to see a number of slack or surplus values. That's why we use that term unconstrained, because theoretically we can do many things, but again, from a practical standpoint, we have to know what our production capabilities are. Now, that being said, it varies by industry. Some industries, if they say we have a plant that can produce 100,000 units, what they really mean in practical terms is we can probably produce 80,000 units, barring days that we have to close the line down to refurbish it, line stoppages, etc. In some other industries where you're having far more complex problems to deal with, you may have an ideal production capability of 100,000 units, but you might at best be able to get up to 70. Okay, so that's the practical value of this problem. Now, the authors want to walk you through the mathematics and all of this, and that's good. But when you see all of these slack resources, it's saying you have all this flexibility. You have to take that with a grain of salt, with an eye to what can I actually do. Okay, now we're going to pop on over here, and they give us some more verbiage about the constraints, and then they talk about the profit contour lines. And you say, what in the world are you talking about? Okay, when we go into a nonlinear situation, excuse me, we can find, what we'll typically find is like what we see here, the optimal solution, okay? And because we're working with something that's nonlinear, we can assume that there are going to be there are going to be 2 or 3 contours out here, okay, that are in terms of the circumference, somewhere along those points, I'm going to find a point where I'm also maximizing the standard. I'm optimal. I'm getting the maximum profit. And that's just simply, again, it's one of those things of an application of geometry. Okay, and you see the contours. And again, this indicates the various levels that theoretically you can get to. All right. Now, the whole practical significance of this course is that if you're in a situation like, making stuff or supply chains or distribution, you have enough knowledge to understand I can produce a mathematical model, but then I have to go back and start to look at the practicalities of it. Now, I'm assuming all of you have had statistics, so I'm praying and hoping that somebody in that course, the instructor, said there's a difference between statistically significant and practically significant. And and what that means is if you have a large number of cases, you could have a very small per case variation, but they will add up and give you a statistically significant result. So you have to be careful of this. And one of the reasons it's important to see this chapter is to understand the nonlinear. Those start to tell us about the limits of what we can do with a mathematical model. Now, I'm going to stop for a second. I've got several of us on here. And so we've got Colton, Isaiah, John, Logan, Robert, Quentin. Thank you so much, all of you, for being here. Who else is here? We've got Sarah, Shane, and Long. I'm going to stop for a minute and ask a question. And here's my question, all right? How might I use these different contours? Now, I have an optimal solution, the high point of this nonlinear line. But how might I use these contours in terms of talking with management or trying to make a decision? And also, anybody have a question about what we've talked about thus far? Anybody, feel free. So we're all understanding it. Well, okay, I hope so. I sincerely do. The truth is, and the authors of the book don't tell you this, you're going to run into nonlinear situations far more than you ever will linear. Most situations are not going to fit linear, and a lot of organizations sub-optimize because they say, oh, let's just treat it like it's a linear function anyway, and that's fine. There's an old saying, data tortured sufficiently will confess to anything. Okay? Now, let's move on ahead. And again, if anybody had any questions, please feel free to stop. And as I mentioned, for example, right here is possible. This is a key passage. I want to make sure I highlight it for you. Okay? They talk about where that can be located, the optimal solution. Now, when we work with nonlinear optimization problems, we also move into the world of local versus global optima. And for all intents and purposes, what that's really saying is that globally, here's an optimal solution like we saw in those contours. But that's not going to be the same necessarily as the local solution, because the local solution is going to be driven by the constraints. Okay? This is why, and it applies to more than just manufacturing. It applies to service establishments. You have to plan for growth. And a rational way to do it is, first of all, to have some really good market research. And then number two, to do some good analyses and build models that seem realistic and understand there's a global and there is a local optima. All right. And again, that deals with functions. Now, here they give you the objective function for a part nonlinear, a concave function. All right? Concave because it's like a cave. But notice this. This is far different than what we've seen before. And as you can see, I want you to stop and think about it. If you remember back in economics, you learned about marginal returns. And as I come up here, I come to a point, that center point, where I've hit the optimal level. I can't do this any better than I'm doing it now. Okay, I'm going to move, and here we start to move down. And this moves us into this will make you a run for garlic or across a convex functions and the quadratic involved. Now you go, oh my goodness. So that's why it's nonlinear. Now, this is a nice little illustration of the kinds of hills and valleys you run into simply because of the questions of resources and constraints. Okay. And the authors are trying to beat it to death, and so am I, so that you understand that you've got local minimums and maximums, global minimums and maximums. And that's really all that's going on. Now, I'm going to diminish this for a moment. And there's Cardinal Buddy. He says, have a good break, everybody. Now I'm going to grab the file, part nonlinear. Here it is. I'll open it up. And I'll enable the editing. And here we go. All right, we've got, this is, and remember this from PAR Inc. Here we have the standard times for deluxe. We have 4 operations: cutting and dyeing, sewing, finishing, inspection, and packaging. Okay? And these 4 operations, I want to talk with you for just a moment about that, because I didn't until I thought it would be appropriate, which is in this point. The operations, typically, if this is done correctly, then you have the operations listed in the order of occurrence so that a person can look at it and they can see in their head the production line, how things will happen, and then begin to plug in the data. Now, when we look here, we see again the time available, the sewing, the finishing. We've been through all that, so those details are no big deal. And then we have the bags produced in terms of standard versus deluxe, and then we maximize the total profit. And then we get our constraints. Okay, and notice something, they're all equal to or lesser than. And then we've got the standard bag price and the deluxe bag price. Now, I'm going to go over here and I'm going to click on data. And I'm going to open up Solver. And here we're going to see that we've got the objective function, okay? And we want to maximize that. And we've got the changing variables. So far, nothing different than what we've looked at before. And then subject to these set of constraints. And then here we make unconstrained variables non-negative. And then we select the GRG nonlinear. Okay? Now, here's what they talk about. And this is one of the reasons I like the Excel tool Solver, because it explains you what do we mean by this. And it's, you know, this works for smooth, nonlinear, and this is, as we saw, concave and convex functions. Okay? And if you want, you could check help for this. You can go out, and I think I had given you some resources earlier in the semester for you that would cover each of these solving methods. Now, what we're using as a methodology or a philosophical approach, that is, I want to optimize, get the best I can given the resources I can, okay? And then the particular method. And we have that nonlinear, and we have the evolutionary, and we have the simplex. So we've got it solved for us, all right? And here's figure 8.2 for us to take a look at. Now you can see again, here's the optimal objective value, and then the reduce, and we're not reducing any costs here, but notice all the slack. Now, we have, interestingly, we don't have a slack or surplus here, but we have a dual value on constraint number 1. And notice that we don't get any of the other data here because we're working with a nonlinear problem, excuse me. So allowable decreases or increases of the objective coefficients, or the right-hand side and left-hand, they're almost meaningless. Now they give us a sensitivity report. Let's click on it. And notice that we don't see any reductions that we get in the reduction gradient. Here's the Lagrange multiplier. You'll want to go out and take a look and learn a little bit about it, so you understand what we're talking about there. And notice that we have a final value, but we have a multiplier. And then we have these other constraints that really give us nothing. And you'll want to go out and take a look at what the Lagrange multiplier is all about. Okay? But that's really all there is for par nonlinear. Now, the par nonlinear file from Chapter 8 files is what I want you to upload for the case for par nonlinear, okay? And so that you'll find the file there in Chapter 8 files, and that's what you need to have upload. You need to upload, or should have uploaded you need to have it done by 5. Now I'm going to close this off, okay? And we're going to take and we're going to head in a different direction, and we're going to talk some more about this case out of the Data Smart book. And so I'm going to go back over here to Vital Source, and here it is. This is the textbook, Data Smart. And as I mentioned, it's over in Chapter 2, Okay. And I'm just going to walk us through this real quickly so we can understand. Now, wait, before I do that, here I want to point a couple of things out to you, okay? What I'm trying to do every week is not only show you the case, all right, and explain it to you as a workshop. Now, you're going to be doing some stuff like this later on when you have a project to do, and you'll probably encounter some questions on the files. So it's not a bad idea to be paying attention or watching these, all right? There's more than me just giving you 15 points of credit. It's to say to you, hey, if you want to know the kinds of stuff you need to be able to do, here it is, or be familiar with or understand. And what I've tried to do is I look through these different cases to select those that I think are going to be realistically the kind of problem you'll encounter in the future when you're out of work. It's not a perfect method that I have, but it's better than none. Now, here's the solution, and I have that explanation for you to take a look at it, okay? And that's where you're going to upload the par nonlinear. Now, the cluster analysis, that's what we're working with. And here, there's some information here on MailChimp, who they are, the guy works in, and Voronoi diagrams, concave versus convex functions. These are the mathematical or scientific models behind what we're trying to do, because we say, you know, the data look like this, and it follows it out of nature. Let me give you a real simple explanation. Example: permutation. If you're in stat and you studied permutation, you understand how 1, 2, 4, 8, or however that's going to work. It's the same with populations. Populations follow a permutation model. That's why a mom and two people get married. They have 2 kids. Those 2 kids have 5 kids between them, et cetera, ad infinitum. So in this case, we have concave, we have a nonlinear solution area, and we even have an optimum, a maximum outside of the feasibility region, because we can get it if we have unlimited constraints. And again, kind of the science that underpins this are the mathematical models that we borrow. Okay, I have some things also I want you to take a look at. Cluster analysis. This is a tool. The SAS has a tool that does cluster analysis. Here's another tool that's out there. It's in your best interest to click on those, take a look at them, maybe play with them a little bit, or learn some, so that when you encounter them at work, for example, maybe you go to work for a company that uses SAS, it's not a surprise. And you can honestly say, well, I've worked a little bit with SAS, not a whole lot, but I'm somewhat familiar with it. Same with JMP software. And there are a lot of different products out there that will do this. Now, there are some of these resources that we're going to use. And I want to open this up for just a moment, the distances. Okay. And I'm going to rotate the page. Hopefully we'll get it clockwise, so I'll get it to where we need to be. Here we go. And I'm going to make it large here for just a moment. Okay. Now, when we're in the cluster analysis, you're going to see some functions that are several functions kind of strung together. And basically, this is just how we determine those distances, and we just simply use the Euclidean formula. But writing out, in terms of an Excel file equation is not for the faint of heart. And I walk you through the math of it. Now, a key piece here, you see the little diagram. And what we're going to do is basically we're going to take each person pardon me, each person who accepted an offer across and then down. We're going to build a matrix. And you'll see here's the matrix. And I give this cell references. And so this is something that I've provided for you just to kind of help you understand what you're looking at. Now, I'll go back for a second here. And let's see who's got a microphone on other than me. Okay. Now, I also provide you with a resource, another one on the distances, pardon me, on the silhouette, because we're going to be looking at that. Again, let me zoom that around for you. All right. Up, and I'll rotate it some more. The silhouette lets us take a look to see distances between clusters, and now I want to walk you through the text and show. He does a good job of showing us some of the graphics of this, and what we're doing when we compute a silhouette. Okay, but understand this: we're taking Euclidean geometry, circumferences, circles, and we're applying that to cluster analysis. And we're using that to model clusters to see if certain people bought a particular wine when it was offered. Okay, so let's open up, let's go back over here to the, we'll go back over here to the book, and we'll walk through here. And you get some stuff on supervised versus unsupervised learning, and a little bit about probability. But here he shows us the initial clusters. And these are people, and he's trying to be funny. He's having, he's talking about a middle school dance or something. But notice he starts off with saying, okay, here are some here's a line of best fit. And what we say is the line denotes or shows us the borders of the clusters. Okay? And that's just, he's just running those parallel. And he shows us down here again in terms of looking at the average distance between each dancer. All right? And then he shows us an optional three means clustering. And so we can work through this. This is an iterative process. Or it's okay, I'm going to assume there's 3 market clusters, there's 4, there's 5. That's one of the powerful things that we can do with this tool. And he gives us then the bag of donuts and pour it. Now, I myself really like how he lays this out for us, and he just shows us simply the details. So I'm going to open up, and it's that wine KMC, and that's the one you'll upload, okay? That's the one you need to upload for credit, for the workshop credit. And here we are, we have the offer information. And the campaign, the type of wine, the minimum quantity, the discount, the origin of the country, where it came from, and is it past its peak? That is, how fresh is it? Okay? And just like with any perishable good, milk, soda, anything like that, they'll have some way to indicate saying must be used before. Liquors are a little bit different, and wine. They have a peak flavor. There's a point where they're at their peak. And you say, okay, well, what about somebody that orders wine that's 150 years old? Is it past its peak? Yes, it is. But because it's been there so long, it's developed some other qualities as the molecules have all interacted. And that's, I guess, the simplest way to put it. And so it has a very different flavor, but and not only is it different, it is unique. And one of the things about wines that you can be sure of is that if you buy different wine, if you buy different wines from the same manufacturer, chances are it's coming from the same vineyard. So you know the source of it. If not, then you could be talking about just one section of a hill. There's some good documentaries on Hulu. You can find them about folks that make port. And then I think the other was some people that manufacture champagne. Now, to me, it's incredible art. And I went through a tour of Silicon Valley, not Silicon Valley, but of the wine country up in California, Northern California. It was incredible to see. I never realized what all that went into making it. So it's just fascinating to me because it's an art married to a manufacturing process. That fine. So next tab, we take the transactions. Okay. And we've got those listed. And we can see we've got multiple transactions. And then we develop a pivot table. Now, I'm going to click on the view here. And I want to see my pivot table. Let's see, I'll put on the data. And I want to see my table. And I'm looking for that. I can never, ever remember where it's going to be over here. I'll find it here in just a second. But and I want the tables. Well, okay. We'll just do it raw here. We got here across the, i.e., across the columns, we have the names of each of the purchasers. And then we have these row labels, okay? And each of these ones, as we talked about, represent a purchase, okay? And of these different offers, all right? Now, we go from that to the matrix. We talked about this some, and I'll move this up for a moment so you can see it. And here we have, let's go to the top, and we have Adams, Allen, etc., and which of the offers Adams responded to. And we're moving to this, where we start to do the cluster analysis, okay? This is the heart of everything here. Now, and then he's going to show us the top deals by cluster, the distances, and the silhouette analysis. And the silhouette will tell us, can I do any better with using 6 clusters or 5 or 4? Because we can name that, we can experiment and name the number of clusters that we want. So we're going to go with 4 clusters. All right. And we're going to use the matrix to see who bought what. And the author also talks about freezing the panes and all that. And so we got all these. Okay. So we'll just go ahead and take them all the way back over here. Now, the next thing we're going to do, and this is what just makes me so amazed at how versatile solver is we're going to use it to compute the distances, and we're going to get the lowest figure possible. And I'm going to click here, and it's a sum of DG to do 8. Okay? And we're now going to take each person and we're going to see what cluster they belong in. So we have 4 clusters here. Then we have all these people who purchased. So we've added in these columns. Now, I'm going to go back over here. I'm going to click on data. Okay. I'm going to click on solver and I'm going to see how we use solver to get the minimum. That's A36 to compute the minimum distance by changing the variables H2 to K33. That's the array that's there. And we're going to have subject to the constraint that they all have to be equal to or less than 1. And because we're not sure of how this will fall out, we use the evolutionary. And just like with the GRG nonlinear, I encourage you to go find out what they're talking about here when they talk about it, the evolutionary. I think the author, I believe he may speak about it some. The truth is what this really means, this is a really fancy way of saying, I'm not sure how this stuff's going to fall out because I'm looking for clusters. And those don't. The closest thing come to were those contours that we had earlier. So we're gonna find out what is the maximum, the minimum, and we solve for it and we get 140.7. Now, you'll notice we have the data that get filled in, and that's all filled in by solver. All right, and those are for the different clusters. Now we start to look at the distance to the cluster per customer, like atoms. And here's where we have the fun of that nice distances formula. And when he puts it in a bracket to start, as opposed to parentheses, he's basically creating a function. And he walks through how to do that. But I want to go back over here for just a second and I'll go back to a vital source. Okay. And well, we're here. I'll just walk you through. There's the list of the offers, pardon me. Here's the pivot table. And I think when we did last time, I showed everybody, I went scoped them back down and covered them, and here they are merged into a single matrix. And he says we start with 4 clusters, and he calls it 4MC. And he shows us here in figure 211 what it's going to look like. Now we're going to come here for a moment and see Euclidean distance. Let's talk about that for a minute. We're talking about data points that have come from the matrix. Here he's using, of course, the dance. And here's a person at cluster 8-2. All right. And here's 4-4, which is the cluster center. Okay. And we're going to see the distance, and we're going to use the Euclidean formula. Pardon me, my brain is dead. The Pythagorean theorem. I'm so sorry, excuse me. Notice what it is. Okay. It's the differences, the square root of the differences. In other words, 8 to 2, and you could look at this like the rise and the run. 8 minus 4 is 4, and 4 minus 2 is 2. Got a question here. Let me hop on for just a second. As I mentioned, I've got it posted over there in the I've got it posted over there the pages, and you're going to find the file over in the Foreman files. And if you go back into the files section, you'll find Foreman, and this is chapter 2. Okay, so we're going to get the different, if you say this sounds familiar, the sum of the differences squared, the square root, we take the differences, we square them, and then we get the square root of that total. And so we're normalizing the data basically. Oh, okay. Thank you. You're welcome. That was a good question. Again, let me review. For the par nonlinear, you want to go into the chapter, I believe we were in chapter 8, and you'll want to pull that out of the Anderson files. In the Foreman student files, this is from chapter 2. And I'm hopeful that you do more than just upload the file to get the credit. If you don't follow it through, or you don't open it up, or have your book open as you go along. Now I do, but of course I'm using this tool. If you have Vital Source, or you have a reader or something like that online, I think it's greatly to your advantage. But we can compute the differences. And you can see we get atoms, and the distance between atoms and cluster 1. And it just becomes that iteration. That's all that's going on. So let me go back here for a moment to the Excel file. All right. And let's look at this. And here we get atoms. This is cluster 1. This is the first customer. And we have that square root, and that's just that same expression we saw written out. But in this case, we're having to use a square root function and embed within that a sum function. And then the sum, then we square that sum. So you can see, and that's the distances. I gave you that sheet of paper handwritten, I did the explanations and all that. That's what that was for. So you can see, well, okay, what do they mean by the distance? How are they doing this? And that's what each component of this formula works out to. Okay. Now we've got the square root. We've got we've got the distance of atoms from cluster 1. Now we're going to say how close is atoms to cluster 2. When we do statistical analysis of any kind, we're always looking for 3 things. 1, measures of central tendency. How much is everything alike? Then we look for things like, then we look for signs of variation. Stuff like the standard deviation, the variance. And of course, the standard deviation is the variance squared. We may even look at error as we do typically with a linear diagram. Okay, so we're trying to look at each of those and figure something out. In this case, we're saying how much does stuff cluster? Because once we've got it, we've identified, we have done a cluster analysis. Now, let me say this. I know it's 1150, and I anticipated I would go over. So if you have to bug out, what you'll want to do is just kind of have a mental note and scroll through to this point, and then you can watch the rest. I'm going to be another 10 or 15 minutes at the most to get this accomplished. We follow the same thing, and notice each time it's just simply what's changing. And then we use the minimum function to choose one which is the closest. I'm going to click on this for a second. And we provide the number or set of numbers in an array. And we find the minimum. And we can check this logically. And we're here at 1.044. So we know that the minimum distance cluster, the minimum cluster distance is 1.044. Now, don't let this fool you for a moment down here. We're going to use the match function. You say, why would I do the max function? Well, so I can drag and drop the thing across. I'm going to click it right here, okay? And I've got the lookup value and then a lookup array, okay? And then if we want a 1, a 0, or a -1 indicating whatever. And what this is going to tell us is the number that the relative position of a number for a specified match. And what it says is, okay, I'm here, and I'm at the second position. And this is just a way for us to build that category. And as you can see, as we come across, we'll see the same thing for Alan. And the same thing for Anderson, Bailey, etc. Now, the next thing he does is he says, okay, what are the top deals by cluster? And he calculates that. Okay, yeah, the file, okay, let me back up and stop for just a moment, okay? The files par nonlinear is from the Anderson text. Let me show you that one. All right, we'll go back here to file source. This is the big book that we're using, the Anderson text. And for chapter 5, in the chapter 8, and then I have student files over there that I've uploaded in the files area. Let's take a quick trip through here, and I'll click in files, and magically you're going to see the Anderson text student Excel files. Now, if you scroll down, and if you've been watching the videos, I think you'd see this by now, but perhaps not. So I'm going to come down here and I'm going to find the Foreman files. That's for the Data Smart. And you'll find Wine KMC in Chapter 2. And I even tell you that at the start of the module. Okay, so we'll go back here, vital source. So that's, and I'll go back to, I want to go back to the Foreman text. Now, when I get questions from people about where do I find the file, you're either asleep or you're not listening. Right now, we're working with two sets of files. One is the Anderson text, and you typically are going, I'll identify the pages out of the Anderson text and so that will give you a clue to the file, because the Anderson student files are organized by chapter. The Foreman, which is the Smart book, Data Smart, the same story. It's in the Foreman student files, and I have them over there in the files section. And then you can see it's chapter 2 in the Foreman text. When I get these questions, it makes me wonder if I don't need to start giving quizzes over these presentations, over these lectures, because when you're asking me how to find it, we're halfway through the course, and we should know this already. Okay, now let's go back here to the Excel file. And here we're going to get the top deals by cluster. In other words, which one occurred the most. Okay, and we're going to run a calculation. And we're just basically taking that distances, and that's that 4MC. When you look here, you're going to see 4MC in single quotes, and then the asterisk, that means the tab named for MC. Same story over here in topic top deals by cluster, and they give us that difference between the two of them. Okay, and we come down and same story down here, and we're just basically saying we're going to see which deal tended to land within a particular cluster, and we do that calculation. Now he shows us the distances over here, person to person. And if you follow this down, every time a person's compared against himself, you'll get a 0. And then he talks about the silhouette. And that silhouette figure gives us a picture of how well we've defined the clusters. And he has a value. See, and then as he follows through in the text, he says, well, let's see what it looks like with 5 clusters. And then we'll see how they work. And then we'll get the silhouette value. Now notice when we worked with five clusters, the silhouette's 0.134, okay? The silhouette over here for 4 clusters is 0.1492. There's not that much difference, so it's a little bit finer cut with 5 clusters, and we are getting a little bit better. So we could say, all right, I'll start with 5 clusters. Could you do 6? Of course you could. You could do as many of them as you want to do. But what you do have now are people who are identifiable by cluster. And we scroll down here. And we can see which person belongs where in what cluster, based upon what they purchased. And that's pretty much it as far as what he's doing with the cluster analysis here in chapter 2 in the Data Smart. Again, he just repeats that same process to identify clusters for people and where to assign them. And so everybody who is a 2, we've got that data. Everybody who fits cluster 1. So at that point we'll want to extract that data and take a look at the clusters and what they purchased, because we know we've got some purchasing clusters here. And that's pretty much it as far as the cluster analysis. And again, that's all over here in the Data Smart book, chapter 2. And in fact, as I said before, I really like the text because he does a good job of showing you tab by tab. That's where we solve for the cluster centers. Okay. Those are all familiar, the objective function, the decision variables, the constraints. Here's the thing. This stuff is not that difficult to understand. Now, what really sets him apart is he's got the creativity to take these different functions to visualize the problem. A cluster analysis is really nothing more than a study of distance. That's really all it is, and using circumferences. Because if things cluster, they meet around a middle point. And again, this just reinforces what the authors tell us in management science. We look for a mathematical model of some type on which we can hang our hat. And then he shows us and then we try to make some sense of them, and we get the 4 optimal cluster centers. And then we get the top deals by customer. So we kind of reverse it on its head. And what we find is that there is a, for the 4 clusters, Pignot seems to be the product where they all gather, at least for cluster 1. And you see, he shows you some of the fuzziness of cluster 3. He goes a little bit deeper here. And then the silhouette is how we can compare K values, that is the cluster center, which in a sense is, and he gives you this average distance to those in the neighboring cluster, average distance to those in my cluster divided by the maximum of each of the 2 averages. So I'm saying, okay, where I'm at in my cluster, am I closer to my neighbors in another cluster than I am in the cluster to which I've been assigned versus the center of that cluster? In other words, am I an outlier? And if I have too many outliers away from the center of a particular cluster, I probably don't have a cluster. And I need to go back to the drawing board. Then the distance metric. So again, with the file and your text, you can follow him. And now, some of the things he doesn't do is explain things like the offset. And the offset equation is pretty simple. Here's the name of the worksheet, and here's the array. Okay, and I'm going to look for this criterion. Okay, and it'll be on my first row. I'm going to go 1 row over, and that lets me get a figure there as far as where that person's at. And you can see here, this is the bare bones distance tab. And then he uses the offset for Allen's deal. And notice that Allen's deal is 0, 1. Adams would be 0, 0. Then Anderson is 0, 2. And we do the drag and drop. And a completed distance matrix, and then the fine cutting that we do. And so the author does a great job here. He does a fine job of taking you through tab. So to really get this, you probably need to listen to the lecture, get the file open, have your book open, and follow him across. Now, I've also provided you some resources there that explain some of these Excel functions, okay? But what we've done here is we've identified tentatively 5 market clusters. When I have 5 market clusters or 5 market segments, I have a sense of how I can differentiate offers. I have a sense of the market, or at least how my customers respond to product offers. In this case, I think these are discount deals. Okay, folks, well, listen, I do appreciate you staying aboard quite a bit of extra time. And again, like we're going to see with 2 or 3 other cases from the Data Smart textbook, it's going to be like drinking out of a fire hydrant. So I really encourage you, to go back and I'll post this. I'll convert this into a video, and I'll post it. And to use the resources I've given you there to explain, well, what is this function all about, or what are we doing in this equation, and see it tab by tab as it unfolds. Okay? Anybody have any questions before I'm finished? Anybody? Okay, well, folks, thank you so much. Be careful on your way home or wherever you're going to be going over the next 2 days. Thanks a lot, and I'll post this. I'll have it posted at the very latest over in the announcements, end of the evening. I think hopefully sooner. Thanks a lot, everybody. Take care now.